Hello everyone. So I welcome you all to the session, and from today we are going to start quantum physics. And this particular segment is quite different from what you already studied in physics or whatever, whether you are a ninth standard student or you are 10th or 11th or 12th or whatever. So whatever physics you have studied so far, that was actually the physics of macroscopic particles. But when we are in the quantum physics, we deal with very small objects which might not be visible and which is certainly not visible through our naked eye. Okay, so that is what its quantum physics is. So, firstly, what will be this lecture flow? Today's lecture flow that I am going to discuss with you. First of all, we will first tell you about the number of lectures and the duration of lecture, and then the what you say frequency of lectures per week, and then I will start with the today's session, which will introduce you with the quantum physics with several topics. Okay, so let's begin. Okay, our our uh, today's topic will be introduction to quantum physics. Okay, and several topics are there in this particular segment. So just to can say for a heading, I wrote introduction to quantum physics. Okay, so let's start. First of all, let's discuss about the lecture plan and all, then we will begin our session. Okay, so first of all, we'll cover this quantum physics in 11 lectures as per the schedule, but you can add 2 lectures, 2 to 3 lectures more as per the need. I'll add. Okay, in betweens, like some problem solving sessions and all. So but decided we have decided to take 11 lectures. That is bare minimum, and surely we will add 2 more lectures uh, because it needs problem solving also. So now frequency of lectures, uh, 2 lectures per week, not more than that. 2 lectures per week. Okay, that will be our frequency of lecture. That is quite digestible also and quite good also. 2 lectures is enough of this particular segment or this particular topic, quantum physics. Okay, now duration of lecture, so as my lectures goes uh, till 1 hour maximum. 60 minutes is the limit to my lectures, not more than that. I'll try to complete this today's lecture also in nearly 50-55 minutes. I'll try to complete. So duration of lecture, you can take as less than equal to 1 hour. Okay, depending on which segment, which topic we are discussing, uh, it will vary. Okay, 30 minutes to 60 minutes, like that. Okay, so this is your description about the lecture. Now anyone can attend. I already uh, told you that anyone can attend if you just want to explore the new dimension of physics, new part of physics, new segment of physics. Then you can just join with me and do this particular segment. As uh, nearly 1 month ago I have started spatial theory of relativities also, which we completed just 2 days or 3 days ago, which lasted for 1 month. And now this particular segment, quantum physics, will last for around 1.5 or 2 months, might be. Okay, so let's begin. Okay. So first of all, what was the need of quantum physics? Okay. We have started quantum physics, but what was the need? Our physics was quite good with classical theories, with the Newton's laws, and more scientists, Galileo's law, and that physics was quite good even. But what was the need? of quantum physics. So actually, the need starts with the limitations that we see in classical physics. Not the limitation in the sense that it is wrong, but in the sense when we explore different dimension of nature, we see different things happening in the nature. Then that phenomenon of nature, some phenomenon of nature, are not explained by using the laws of classical physics. Okay, so actually, what happened that we were good with classical physics, but in classical physics we were just discussing about macroscopic particles. The main, you can say, if I have to just connect classical and quantum physics, why we devised quantum physics, or why quantum theories of quantum physics came, and already we have had classical physics, theories of classical physics, but still we need quantum physics. Why? Because actually in classical physics we discuss about macroscopic objects. Okay, what do you mean macroscopic? There are two types of object generally, micro and macro. Micro is, as the name suggests, it can be seen through microscope. It is not visible, or you can say it is rarely visible by naked eye. Macroscopic objects are the objects which are visible by our naked eye. An object, if macroscopic object, you can define by their dimension also. That their dimension are non-negotiable, or non-negotiable, not non-ignorable. Non-ignorable. Okay, like it is in centimeters, millimeters, meters, kilometers, then these are not ignorable quantity. But this was with classical physics. But again, we have two types of object as we discussed. Microscopic objects are also there. So you can understand that classical physics, we cross the bridge from classical physics to quantum physics in the search of physics for microscopic particles. In more specific way, if I say microscopic particles. What are microscopic? That are not visible by our naked eye. Their dimensions are ignorable, but their dimensions are in the units of picometers, angstroms, and femtometers. That is very, you can say, nanometers, right? So they are in the 10 raised power minus 9 minus 10. So that value is very negligible, but the physics of that particular microscopic object we have, we don't have. Okay, but we devised it through, you can say, but through time it was devised. So actually from classical physics, we just, it's you can say a very big branch, but some, you can say, assumptions were there in that in that tree. You can say a big tree. Classical physics was a big tree. That it is a very good, you can say, part of physics. But there was something missing there, so we delved into two things. From classical physics, we covered, you can say, two segments. Mainly, classical physics was there, but then in modern times we have had two dimensions. That is relativity, and even these relativity, or whatever you say, quantum physics, little quantum physics will be a little different segment, but relativity is, you can say, inspired by classical physics. Even all the laws or all the concepts are inspired by classical physics at some extent. Some, like relativity, it suppose, you say, inspired by 10%, suppose. In quantum physics it is 3%, 4%, but actually the main, you can say, foundation is of classical physics only. Then comes relativity. Why? To just enhance the beauty of physics. Nothing more. We are not here in the matter of controversy that this physics is good and that physics is bad. No. Just to enhance the beauty of physics. Just to enhance the, you can say, to get the different dimension, to get the different view of seeing the nature. These concepts came. That is the relativity and quantum physics. So relativity was, because to deal with very high speeds, very high speed moving objects, like like uh, speed of light. Light equal to the speed of light. Speed equal to that c. So to deal with that, relativity was devised, and you all know our you can say the great Albert Einstein has uh, made this particular theory very well in the two segments, special and general theory of relativity. Talking about quantum physics, see relativity. You can say that relativity was by one scientist, Albert Einstein. Even some more little you can say mathematical we have taken from Lawrence also, but still you can say on a broader level you can say that yeah, uh, Albert Einstein. But quantum physics, talking about quantum physics, it is not a result of one day, or it is not a work by one scientist. Many scientists, even Einstein has given his photoelectric experiment, has photoelectric theory in this particular quantum physics, and he has got a Nobel Prize for that also. So that's what quantum physics is a very big. It has scientists like you say Niels Bohr, you say James Rutherford, I think his name was. We have J.J. Thomson. We have had D. Broglie. We have had Schrodinger and many more. They are responsible, and they are even the main, you can say, the person who has created this particular beautiful part of physics, that is quantum physics. Okay, so this we are going to now discuss today. From today, we are going to start this particular segment of physics. So quantum physics, as I said, it deals with microscopic objects whose dimension are in nanometers, picometers, and femtometers. Okay. Okay. I think everyone is ready to start with me this particular beautiful part of physics, that is quantum physics. So uh, I decided to start with such a beautiful illustration to just cover the bridge between classical and quantum physics. Because if we will directly jump from classical to quantum physics, and we'll discuss the photoelectric effect, and we'll discuss about photons and all, then it might feel some, you can say, awkward. But if we will just cover that bridge, then it will be very good. Let's start. So we will discuss with an illustration. This illustration is will give you idea of many things. So this illustration is like this. Identical experiments need not give identical results. Fine. Now, it's not fine actually. We have not understood what actually it does it mean. Just it is a statement which we are now going to verify through an you can say what do you say example, right? So this is an illustration where this is a statement, and now we will just illustrate it. So identical experiment need not give identical results. What does it mean? Firstly, let me superficially tell this. Identical experiment need not give identical result. Identical experiments means experimental setup is almost same. Almost. I'm using the word not same, because if I use same, if I write same experiment need not give same result, same experiment will give same result. Identical experiment. What do you mean by identical, and what do you mean by same? Identical means not actually same, but just approaching that. So we will make just a little, you can say, alteration in experimental setup, little, very little. That is ignorable also. That is called identical experiment, and then we will see that the results, the final results are not identical. It varies. So let's see. So this is a medium. So we have this medium, or even not considering medium, we can directly consider a surface also, where we can have two phenomena. This surface is smooth, and this surface is also acting as interface. What do you mean by interface? A surface separating two different optically, you can say two different media who have different optical density. So this is a medium of optical density n1, and this is medium of optical density n2, or refractive index, whatever you say. Little difference is there in between them, but let's take it same. Okay, so a beam of light is incidented on this particular surface, that is acting as interface also, and that is acting as what happened, smooth and interface. Okay, fine. Okay, so our beam of light or ray of light is incidented on this particular, this is O point, this is A point. Okay, now you see, this is normal. I think basics of optics you all know. Okay, fine. So this is angle of incidence. Now when a ray of light is incidented on the surface is smooth, so it will go for reflection. That's clear, because surface smooth. If surface was rough, then also reflection occurred, but that will be regular reflection. Here we will have regular reflection, regular reflection. So reflection will be there, and suppose this goes for reflection also with angle smaller. Now we are also given with this. Suppose this is N2 medium. This is N2. Wait. Just give me 5 seconds. Right, I'm making it correct. Okay, N2. Fine. So we will consider that light goes from rear to denser medium. So N1 is represent N2 like this. Okay. So here light ray will bend towards the normal like this. This angle will be R dash, that will be angle of refraction. Fine. So angle of reflection, angle of incidence, angle of diffraction. Now this A is what? This is a source, and the light which is coming from the source, its intensity is fixed. The number of constituent particles of that particular light beam is also fixed. But how many of them will go for reflection? How many will go of them will go for refraction? That is not fixed. Okay. So suppose 100 photons are coming, and one thing I want to say, that if you don't know photon, just wait for 4 lectures. See, whenever you see any movie, at the starting phase you don't know the whole story, but once you progress with 1.5 hour 2 hour, you start relating things. So just my lectures are in that way. Okay, so yeah, you will relate this. If you don't know photon, if you know photon, then you can relate right now also. Suppose 100 photons are coming from this particular source A. Now we will made an experimental setup. Suppose an experimental setup like this, and in second experiment we can take as you can say N1 as a denser medium and N2 as a rarer medium. We can take, so we have taken two experiments, suppose E1 and E2, and that 100 is fixed. Experiment is identical because the surface is smooth, interface it is acting as an interface. Just at optical density there is a variation. Just variation is in optical density, no issues. So if we talk about reflection and we talk about refraction, suppose in even experiment 40 photons go for reflection and 60 goes for refraction, and this changes to like this 30 and 70 in the E2 experiment, or whatever be the you can take more experiment also. So experimental setup is identical, experimental setup is almost the same with a little variation, but the results are coming different. Results are not coming identical, results are coming different. So this tells us that we have created a same experimental setup almost, but the results are coming different. So identical experiment need not give identical result. It means need not give. Need not means it's not compulsory, but it might be also. There might be an experimental setup where even and E2 will show the same results. Might be, but it need not be. Okay, it need not be give the same results. So as you can see, this is one experiment. You can say this is an observation. We have taken observation table, and you can see the clearly the variation. So from the source, it is fixed that 100 photons will come, but how many will go for reflection, how many go for refraction, that is not fixed. So hence we can say that identical experiment need not give identical results. It will depend. Okay, fine. So this was our concept of that particular. We have just verified that statement through an illustration. Now let's make a generalized mathematical equation for this case. We will consider here a now medium, and a ray of light will be incidented on this particular medium. Fine. And angle of incidence will be I, angle of reflection will be R. And suppose this from a source, you can say light of Pi power is coming, incidented power is Pi. See, we can see it in intensity form also. Intensity is power over area, and intensity we explain in the terms of photon. Okay. So in short, you understand in terms, you can understand in terms of photon also. So Pi for this reflected ray, we can say PR. For this refracted ray, we can say PT, and this medium may absorb some of the photons, so we can say that is PA. That is an absorbed power. I'll name this all. Don't worry. So what happened? Same case as we discussed. 100 photons came. Some went for reflection, some went for refraction, that is transmission, and some were absorbed. So that Pi is the main, and it has three branches, that is PR, PA, and PT. So you can write mathematically. Pi is PR plus PA plus PT. So Pi is incidented power. Yeah, you can say uh, source of light has the power this, you can say. And this PR is the reflected power. This is power absorbed, and this is transmitted power. Just divide the equation by Pi. Divide by Pi. You will get 1 is equals to PR by Pi, PA by Pi, PT by Pi. Fine. So 1 is equals to A plus R plus 1. Wait, let me be clear here. Uh, wait. R plus A plus T, right? R plus A plus T. Wait, here we are just. Okay, so see, A plus R plus T is equals to 1. Fine. Now, this is your general equation. Okay. It is, what are the possible values of A R T? It will always lie in this closed bracket, 0 to 1. Fine. 1 means 100%, 0 means 0%, 1 by 2 means 50%. That is, I think you know. Now we will discuss about some special bodies which will have absorptivity 1. Hey, sorry, one thing I missed. What is A? A is called absorptivity. That is PA by PI. R is called reflectivity. That is PR by PI. And T is called transmittivity. PT by PI. Fine. Now, now we will discuss about black body. What is black body? First of all, you have to write this is a body need not be of black color. The first confusion comes here. That first confusion here you will have that it will be of black color. Not really. It can be of any color. Okay. So black body need not be of black color. Okay. Any color it can be. But what is the you can say speciality about this? Absorptivity will be 1, and R and T will be 0 as per the equation we have to follow. So absorptivity will be 1. For black body, they are good absorbers. They are good absorbers. Fine. Okay. Now you may wonder that we see gold, we see diamond, they shine. golden just shines. So why? What's the reason? Because their R is 1, their reflectivity is 1, and A and T are 0. So even if you will place them in dark, even there is no light source, no issues. They are a good reflector by their own. They can reflect their own light. So just they will shine and shine. So that's the reason is reflectivity is 1. So that's why gold and diamond shines. Fine. Okay. Now we will discuss about Kirchhoff's law. Okay, there are several laws now. Kirchhoff's law, means displacement law, Stephen's law, Newton's law of cooling. These 4 laws we are going to discuss. So be patient. Already we are with the 25 minutes, but as I said, lecture will be a little lengthy today because this will form the base. Reason is that this will form the base for you in the further quantum physics. So let's discuss these laws. First of all, Kirchhoff's law. What does Kirchhoff's law say? Good absorbers are good emitters. Good absorbers are good emitters. What does it mean? A is equals to E. What is E? We have discussed A. E is called emissivity. So for black body, for black body, A equal to E equal to 1. This you must know. Okay, so that is basic of Kirchhoff's law. These laws are very less. You will take. I'll discuss with you in 3 minutes, 4 minutes. Okay, and then we will proceed to the main topic. Okay, now we will discuss Stephen's law. Stephen's constant name. Stephen's law. Okay, Stephen's law. What does it say? Emitted power directly proportional to temperature is to the power 4. So when we remove this proportionality sign, then we have constant like sigma E A to the power. Now sometimes we write it in intensity form also, that is PE by A, that is intensity, or you say it is a spectral intensity, or you can not a spectral, you can use it by small u also. Okay, it is noted by small u also. Okay, so that way also you can write, or you can write in this way also, sigma A to the power 4. The sigma is called Stephen's constant. A is area of cross section. T is temperature of that particular body. Fine. Now the value of Stephen's constant is very less. As I remember, it is in this way, but you can check. I am not betting that I am saying correct. Very less value. No need to remember also. Sigma EA T raised to power 4. This is PE. For black body, you can write. For black body, what happens? You say E as 1. It becomes sigma AT power. Fine. Okay. Good. Now we will discuss about next law. That is your Wien's displacement law. Wien's displacement law. What does it say? The wavelength corresponding to the maximum spectral intensity, product of that wavelength into temperature, will be a constant, and that constant will be called as Wien's constant. And it also has very small value. You can check. So what is lambda m? We will discuss now through a graph. Okay, so let's take a graph. Suppose the graph is between spectral intensity, that is u lambda, or you can say this is spectral intensity corresponding to lambda wavelength. Okay, now just plot two graphs in this way, like this. This axis is temperature, this is T1 and this is T2. As you can see here we are with the maximum, the wavelength corresponding to maximum spectral intensity. Let's name it u lambda 1 and let's name it u lambda 2. So as we can see, it is corresponding to that particular wavelength. So this particular spectral intensity will correspond to that particular wavelength, that it will correspond to at lambda 1 and this will correspond to lambda 2. So as we can see that as temperature increases, that T1 is less than T2, lambda 1 is actually what? Lambda 1 is coming greater than lambda 2. So from here also you can say very simply that lambda 1 also, you can lambda m1, you can write maximum, it is corresponding to the maximum spectrum intensity lambda m1 and lambda m2. You can write lambda m1 or lambda m is inversely proportional to the temperature. Fine. Or you can say the product is constant, means constant. Okay, now this was Wien's displacement law. I think it is done, and now we will discuss about the one more law, Newton's law of cooling. So now we will discuss Newton's law of cooling. So as name suggests, cooling means there will be decrement in temperature. So we will write as rate of fall of temperature is directly proportional to temperature difference delta T. And this temperature difference is between the that body's temperature and the surrounding temperature. That is, we will use at T as body's temperature and Ts as surrounding temperature. So we can write it in this way mathematically. We can write it in this way that this is equals to a constant C dash into temperature. Temperature difference will be given by T minus Ts. This is a raw equation. It's a raw equation. But actually what happens when you will just manipulate this, it will be, if you take initial and final temperature as Ti and Tf, it will be Ti minus Tf over T is equal to C dash, and this T is not actually T, this T is the T average, means average of these two initial and final temperature. It's Ti plus Tf over 2 minus Ts. That's as simple as that. Okay, so this is your equation of Newton's law of cooling. This is the mathematical interpretation. Okay, now I think it is clear to you Newton's law of cooling. So with this we are almost done with the laws, and now we will discuss about the photon and energy of photon. So what is photon? So if you will ask just one who reads book, any book where we just introduce you with photon, or even you see NCRT also, when you will study NCRT of 12th standard, I think chapter will be your 12 nature of radiation matter. That is the chapter name. 11th or 12th. Chapter number is 11th or 12th. Okay. There you will study about photon. What they will say that I'm writing here, and then how many corrections are there that I tell you. They say photons are massless particles, and having energy, or they write as energy packets. This is correct. This is also correct. This is not correct. Photons are not massless particles, strictly speaking. But if you are speaking superficially, it is correct. But strictly speaking, they are not massless particles. Okay, but see, wherever it is written massless, what does it mean actually? Sometimes we just say the things are wrong. See, if you write massless particle, then I'll say it's wrong. Okay. Because strictly speaking, I always see all the aspects, and then I'll just judge you that whether you are saying correct or not. So this is statement, if you write, if I see all the dimensions, if I use it in a deeper sense, then that is wrong. But why they write massless particle? What does this actually mass mean? What which type of mass, what type of mass they are talking about, that they say massless particle, that we are going to discuss. Okay. So first of all, remember this. Remember this. We have had two types of mass. One is denoted by small m. See, denotation can be changed. You can denote it by different, but what I am denoting, that I am saying you small m, and that is one is small m and not m not. Okay, in subscript. This m is called as relativistic mass. What does it say? What we say, relativistic mass. And this m naught is called as rest mass. Okay. So what they say, that massless particle, their photons are massless particle, they mean rest mass. So yes, for photons, surely m naught is zero. But this mass is rest mass, not, you can say they are massless particle. They have mass zero, but that mass is called rest mass. That is not actually, because if we will see in that, there are two terms, relativistic and rest mass. So if we are just saying mass, it means relativistic mass. Okay. M, small m. But when you are saying mass at rest, that is rest mass, you can, if you will just write mass is equals to zero, that mass will be called as relativistic mass. But if you have specified that it is a rest mass or it is m naught, then you can say that yes, for photon m naught is zero, means photons are not massless particle, but photons have their rest mass zero, means they are called massless particle when they are at rest. So, because at the rest, we will use some mathematical equation also to understand this. So let's use that also. But first of all, understand about the, we say they are energy packets. Why they are energy packets? Photons are the constituent particles of light. This you may know from your low junior standards, or just a very basic thing, that if this is a light beam, suppose, or ray, whatever you say, and their constituent particles, they are called photons, constituent particles. And now light beam is moving with the speed of light, that is c. So that photon will also move with the speed of light c. Hence the speed of light of photon is c. Fine. Now we will use an equation which we derive from using the Lorentz transformation in relativity. That is m is equals to m naught into gamma. This gamma is called Lorentz factor, that is m naught by root under 1 minus v square by c square. Okay. Now, now for photon, v is tending to c. V is not v light c. It is little vague. Mathematically, we will say v tending to c. So v square by c square will tend to 1. Okay. 1 minus v square by c square will tend to 0. In numerator we have 0, here we have tending to 0. So it will result in what? Mass is 0 by tending to 0. This will be not, or you say indeterminate. 0 by 0 form, or you say uh, infinity by infinity form. These are the forms called indeterminate form. There are 7 indeterminate form. I will not discuss about that. That is part of limits. So mass, relativistic mass is not mass of photon is not. Okay, fine. So from this, sometimes when we say mass is not defined, you will say that then how can we write the momentum of photon? Because when we are writing momentum, term of photon, momentum, what we write, mass into velocity. No issues. But here we are saying mass is not defined. Strictly speaking, it is relativistic mass. It's not defined. The momentum of photon will not define. but actually this is not the case. This is not the scene. Momentum is defined, and that momentum, what will be the momentum, that we will discuss. Okay, so that momentum is actually, for photon, that momentum is energy of that particular photon over speed of light. When you will divide that energy of photon by speed of light, then you will get the momentum. But for that, we have to understand uh, energy of photon. Okay, so now we will discuss that. So, energy of photon. So, experimentally, it is found that energy of photon is varying directly. You can say it is in the directly proportional relation with frequency of radiation. So, EP is directly proportional to nu. Now you will remove the proportionality constant, it will be h nu. What is h? Planck's constant. H is called Planck's constant. Value of Planck's constant 6.6 into 10 to the power minus 7 minus 34 joules second. EP is equals to h nu. Now sometimes you will see that we say, generally speaking, that energy of photon is inversely proportional to wavelength, or even the people derive also from that particular, they write that EP is directly inversely proportional to lambda, then comes to constant hs. That's not the case. Experimentally, we say this is found. What we do 1 by lambda, that is mathematical. Experimental is different, mathematical is different. We will make mathematical manipulation also here. That's the thing. So this h is called Planck constant. So which Planck constant? There is one more associated term, that is reduced Planck constant. And remember, when we are in the quantum physics, then we have to introduce some more terms. Might be even I have taught, as I remember, I taught atomic structure in chemistry also. In that portion, we were with this portion only. I think there I extended with the h cut, reduced Planck constant. But generally, we are limited to this particular formula. But here, when we are in this, uh, you can say quantum physics, then we have to understand that term also. And that term is called reduced Planck constant. What is reduced Planck constant? H cut. Okay, and this h cut is obviously its value is less than Planck constant, that is h over 2 pi. And from here h you can write 2 pi h cut. Okay, and now you will write energy of photon in terms of h cut. H nu. H cut 2 pi nu. What is 2 pi nu? Angular frequency. If you don't know, I'm telling you, angular frequency is 2 pi by time period, or you can write 2 pi into frequency. H cut into omega. This is omega, called as the symbol omega, but called as angular frequency. So energy of photon now comes as h cut into omega. Fine. Done. Ready. Now, we will just say make its mathematical formulation in terms of wavelength. So let's try. EP is equals to h into nu. Now you just write nu in terms of lambda, that is h, that is c by lambda, so hc by lambda. And here this energy will be in joules, this lambda will be in, and this all will be in SI units. And remember, h, the product of Sc is 2 into 10 to the power minus 25 in SI units. These are some values which you must know, because it will help you in problem solving simply. EP is equals to hc by lambda, or you write h nu, where the all are in the SI units. But when we are, as I said already, as I said, that we are dealing with quantum, you can say, physics. So here the particles are very small. So these SI units are very big for them. So we will introduce some more units. Like here we will introduce another unit of energy, that's electron volt. And what is actually electron volt? 1 electron volt is actually 1.6 into 10 to the power minus 19 joule. It is very less. It is very much less than 1 joule. So generally, when we say photon of 5 electron volt, 10 electron, we will not say 5 joule, 10 joule. That is not there. they have very less energy, 5 electron volt, 10 electron volt. So we will discuss in that sense, that 1 electron volt. Okay, so we will deal it electron volts. Also, lambdas we will take in nanometers or we take in angstrom generally, or some other, but these are the two frequent used units, nanometer and angstrom. So now we will just form the formula in the these sense. So EP is equals to Hc by lambda, and this you have to remember that it is 1240 electron volt nanometer over lambda in nanometers. But if you take it angstrom, then it will be 12400 by lambda in angstrom, and this will be electron volt angstrom. Fine. So these are the formula which you must remember. Simply you have to just write Sc, 2 into 10 to the power minus 25. Just uh, you say divide it by 1.6 into 10 to the power minus what, 19, I think, right? And you will get this, I think, because you see Sc is 2 into 10 to the power minus 25 joule, or whatever SI units. Okay, and then you can just convert this SI unit into electron volt, because 1 electron volt is 1.6 into 10 power minus 19 joule. 1 joule will be 1 by 1.6 into 10 to 10 power 19. So in this way you can do that. Sometimes it is given that EP is equals to suppose 3.2 into 10 to the power minus 16, 1.6, 3.2 into 10 to the power minus 90. Suppose it is given that energy of photon is 3.2 into 10 to the power minus 19 joules. Suppose it is given. How you will convert it into electron volt? You will just divide it by 1.6 into 10 to the power minus 19, and it will be electron volt, that is 2 electron volts. That's the basic conversion. Okay. So yeah, with this we have completed the agenda of today's lecture, and in next lecture we will talk about photoelectric effect. That will be very important that is very important segment of quantum physics, and you have to just revise these all topics. Okay, especially the topics from photon energy of photon. These are the very important things, because we will use it as a prerequisite, or you can say as a foundation, to understand photoelectric experiment and photoelectric effect. Okay, so uh, let's so thank you so much for joining me in this session, and in next session we will discuss about photoelectric effect. So uh, 2 lectures per week will be there, and this first lecture will be on 11th May 2026, sorry, and 4 p.m. IST. Okay, timing. Bye bye, take care, and exiting 1 2